Hello there, and welcome back to Bedtime Science. I'm really glad you're here tonight. The Milky Way is not just the pale river of light that crosses a dark sky. It is the enormous rotating structure that contains every familiar star, every planet in the night above you, every nebula bright enough to photograph, every dark cloud that hides new suns, and the small yellow star whose light made Earth possible. It is not a distant object outside your life. It is the place your life is happening. A galaxy is not still. It is a moving city of stars, gas, dust, magnetic fields, ancient stellar bones, newborn systems, invisible dark matter, and long gravitational memories. The Milky Way has been assembling itself for almost the entire age of the universe. It has swallowed smaller galaxies, stretched streams of stars around its halo, built spiral arms from waves of density, formed generations of stars, and scattered the elements of dead suns into the clouds from which new planets are born. What makes it strange is that we study it from the inside. We cannot step outside the Milky Way and look back at it. Every map of our galaxy has been reconstructed from within its disk through dust, distance, motion, radio waves, infrared light, parallax measurements, stellar chemistry, and the patient tracking of billions of stars. To understand the Milky Way is to understand a structure so large that light itself needs 100,000 years to cross it, while standing inside it on one planet, around one ordinary star, in one minor arm. The Milky Way is a barred spiral galaxy. This classification tells you its three most important structural features. It is a galaxy, a gravitationally bound system of stars, gas, dust, and dark matter. It is a spiral. It has a flattened disk with arms of higher stellar density curling outward from the center. And it is barred. It has a central bar-shaped structure of stars running through the central bulge, from which the spiral arms extend, rather than arms that begin directly at the center. The bar is approximately 27,000 light-years long, oriented at roughly 44 degrees to the line between our solar system and the galactic center. About 2/3 of all spiral galaxies in the observable universe are barred spirals, and in the 1990s and early 2000s, improved infrared observations confirmed that the Milky Way belongs to this majority. The Milky Way has four major spiral arms. The Norma arm and the Scutum Centaurus arm originate from the ends of the central bar. The Carina Sagittarius arm and the Perseus arm are the two other major arms. The Sun sits in a minor arm sometimes called the Orion arm or Orion spur, a shorter, less prominent feature connecting the Perseus and Carina Sagittarius arms. Our position in a minor rather than a major arm may be relevant to the stability of the solar system. The major spiral arms contain higher concentrations of molecular gas clouds, star-forming regions, and massive stars that end their lives in supernovae, all of which represent potential perturbations to planetary orbits and sources of radiation that could be hazardous to life. Our quieter suburban location in a minor arm has given the Earth a relatively stable and radiation-moderate environment for the past 4.5 billion years. The disk of the Milky Way is not flat. It is warped, bent upward on one side and downward on the other, in a way that becomes increasingly pronounced at larger distances from the center. The warp of the galactic disk was first detected in the 1950s through radio observations of hydrogen gas, and has been confirmed and characterized by subsequent surveys. The warp extends across the outer reaches of the disk, where the gravitational influence of the central mass is weaker and the disk is more susceptible to distortion. The cause of the warp is thought to involve the gravitational influence of the Magellanic Clouds, two dwarf galaxies that orbit the Milky Way and whose gravitational pull on the outer disk has bent it over time. A 2019 analysis of Cepheid variable star positions confirmed the warped shape in 3 dimensions with considerable precision, revealing that the warp is also rotating, precessing, around the galactic center over time. The thickness of the Milky Way varies with position. The thin disk, which contains most of the galaxy's gas, dust, and young stars, is approximately 1,000 to 2,000 light-years thick. The thick disk, an older, kinematically hotter component of the galaxy containing older stars with higher velocity dispersions, extends to about 3,000 light-years above and below the midplane. The central bulge, which is roughly box-shaped rather than smoothly spherical and contains mostly old stars, rises about 10,000 light-years above the disk plane. And surrounding all of this is the stellar halo, a roughly spherical distribution of old stars, globular clusters, and dark matter extending perhaps 300,000 light-years or more from the center in all directions. The halo is ancient and diffuse, populated by the oldest stars in the galaxy. The central bulge of the Milky Way is dominated by old stars, stars that formed in the first few billion years of the galaxy's history, and is thought to have been assembled early in the galaxy's evolution through a combination of rapid star formation and the merging of smaller stellar systems. The bulge is not smooth and spherical, but has a complex, boxy or peanut-shaped structure when viewed edge-on, the result of the dynamical evolution of the bar over time. In the innermost few hundred light-years of the galaxy, star densities are extraordinarily high, orders of magnitude higher than in the neighborhood of the Sun, and the environment is violent by comparison, with powerful magnetic fields, hot ionized gas, and energetic phenomena associated with proximity to the central supermassive black hole. At the very center of the Milky Way sits a supermassive black hole called Sagittarius A star. Its existence was first inferred from the motions of stars in the galactic center, which were moving at speeds and in orbits that could only be explained by the gravitational influence of an enormous concentrated mass. In 2002, after years of painstaking observations tracking the orbits of individual stars near the galactic center, Reinhard Genzel and Andrea Ghez, who shared the 2020 Nobel Prize in Physics for this work, confirmed that the mass responsible for the orbits was concentrated within a region smaller than our solar system. The best current estimate of its mass is approximately 4 million times the mass of the Sun. In April 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, a ring of glowing gas around the shadow of the black hole, confirming the direct observation of the galactic center's most massive object. The star S2 holds the record for the fastest measured orbit around Sagittarius A star. It completes a full orbit approximately every 16 years, and at its closest approach to the black hole, a distance of approximately 120 astronomical units, somewhat comparable to the distance from the Sun to the outer solar system. It travels at nearly 3% of the speed of light, roughly 27 million kilometers per hour. Observing S2 and its fellow S stars over multiple complete orbits has allowed the mass of Sagittarius A star to be calculated to high precision and has provided tests of general relativistic effects in strong gravitational fields, including the detection of gravitational redshift in S2's light at closest approach. These stars, orbiting a black hole at the center of the galaxy in periods of decades, are the closest natural laboratory for testing fundamental physics in the most extreme gravitational environments accessible to observation. Sagittarius A star is currently quiet, relatively inactive compared to the central black holes of other galaxies, many of which are actively accreting material and producing enormous outflows of energy. But the galactic center shows evidence of past activity that was far more violent. The Fermi bubbles, two enormous lobes of gamma-ray and X-ray emitting gas extending approximately 25,000 light-years above and below the galactic plane, were discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope. They represent an outflow of energetic material from the galactic center that occurred millions of years ago, and their energy suggests either a major episode of star formation in the galactic center or a period of active accretion by Sagittarius A star, or both. The bubbles extend well beyond the galactic disk into the halo, and similar structures have been observed in other galaxies with more active central black holes. Whatever produced them, it was among the most energetic events in the recent history of the Milky Way. The Milky Way is approximately 13.6 billion years old. This is close to the age of the universe itself. The Big Bang occurred approximately 13.8 billion years ago, and the first galaxies are thought to have begun assembling within the first few 100 million years. The oldest stars in the Milky Way, found in globular clusters in the halo, have ages measured by isochrone fitting of their Hertzsprung-Russell diagrams that place them at approximately 13 to 13.5 billion years old. The very oldest known star in the galaxy, HD 140,283, a metal-poor subgiant visible to the naked eye in the constellation Libra, has been estimated at approximately 14.46 billion years old, with an uncertainty of approximately 0.8 billion years, consistent with an age just slightly less than the universe. These ancient stars predate not only the formation of the solar system, but most of the enrichment of the interstellar medium with heavy elements that make rocky planets and complex chemistry possible. The history of the Milky Way is a history of growth through mergers. The galaxy we inhabit today was assembled from smaller structures, protogalactic fragments, dwarf galaxies, and streams of infalling material over billions of years. A major event in this history was the merger with a galaxy now called Gaia Enceladus, or Gaia Sausage, which occurred approximately 8 to 11 billion years ago. This was a significant collision with a galaxy roughly the size of the Large Magellanic Cloud, and it contributed an estimated fraction of the stars now found in the inner halo and thick disk of the Milky Way. The merger disrupted and heated the pre-existing disk, contributing to the formation of the thick disk, and deposited a population of stars with distinctive kinematics, highly radial orbits, moving preferentially toward and away from the galactic center rather than in the roughly circular orbits of disk stars that are now identified in large stellar surveys as the debris of the ancient collision. The Gaia Space Telescope, which has mapped the positions and velocities of approximately 1 billion stars, revealed the structure of this ancient merger in extraordinary detail. The Milky Way continues to interact gravitationally with its satellite galaxies. The two Magellanic Clouds, the Large Magellanic Cloud and the Small Magellanic Cloud, are the most massive of the approximately 60 dwarf galaxies that orbit the Milky Way. They are visible to the naked eye from the southern hemisphere as faint, detached patches of the Milky Way. The Large Magellanic Cloud is approximately 160,000 light-years away and contains roughly 20 billion stars. The Small Magellanic Cloud is approximately 200,000 light-years away and contains roughly several billion stars. Both clouds orbit the Milky Way on highly elliptical trajectories and are connected to the Milky Way by a stream of gas, the Magellanic Stream, that stretches approximately 150 degrees across the sky, marking the trail of gas pulled from the clouds by the Milky Way's gravitational tidal forces over several billion years of orbital interaction. The fate of the Magellanic Clouds is gravitationally determined. The Large Magellanic Cloud is estimated to merge with the Milky Way in approximately 2 billion years, well before the Milky Way itself merges with the Andromeda Galaxy. This collision, when it occurs, will be significantly more disruptive to the Milky Way structure than the previous mergers encoded in the halo's stellar populations, because the Large Magellanic Cloud is relatively massive. Simulations of the collision suggest it may trigger a reactivation of Sagittarius A star, as gas is driven toward the galactic center, the black hole may begin actively accreting material, briefly transforming the otherwise quiet Milky Way center into something resembling a low-luminosity active galactic nucleus. The collision will also scatter stars throughout the halo, disturb the disk, and potentially trigger new star formation from the gas stripped from the Magellanic Clouds. The Andromeda Galaxy, Messier 31, is the most massive member of the local group, the group of approximately 50 galaxies to which the Milky Way belongs, and it is approaching the Milky Way at approximately 110 kilometers per second, driven primarily by the mutual gravitational attraction between the two massive galaxies. In approximately 4.5 billion years, the two galaxies will begin their merger, which will unfold over hundreds of millions of years. Because stars are sparsely distributed within galaxies, direct stellar collisions during the merger will be extraordinarily rare. The probability of any specific pair of stars colliding is vanishingly small. But the shapes of both galaxies will be completely transformed. Tidal forces will pull stars into long streams. The central black holes of both galaxies will spiral together over millions of years, eventually merging to produce a single, more massive black hole. The two spiral galaxies will emerge as an elliptical galaxy, a structure qualitatively different from either parent. The star formation rate of the Milky Way is currently estimated at approximately 1 to 3 solar masses per year, meaning the galaxy produces roughly 1 to 3 new stars equivalent to the mass of the Sun each year. This is a modest rate by cosmic standards. In the early universe, at the peak of star formation activity roughly 10 billion years ago, galaxies similar in mass to the Milky Way were forming stars at rates tens to hundreds of times higher. The Milky Way is past its peak of star formation, its gas reservoirs having been partially exhausted by 10 billion years of star production. The molecular clouds in the spiral arms are the remaining raw material, and the star formation occurring there today, producing the young, hot, blue stars that trace the spiral arm pattern, represents the final chapters of the galaxy's most productive period. Star formation in the Milky Way occurs in cold, dense molecular clouds, regions of interstellar space where hydrogen gas has cooled to temperatures of 10 to 30 Kelvin and formed molecules, primarily molecular hydrogen with admixtures of carbon monoxide, water, ammonia, and more complex organic molecules. These clouds range in mass from a few solar masses to 10 million solar masses, and the largest, the giant molecular clouds, are the primary sites of significant star formation. The Orion molecular cloud, visible to the naked eye as the fuzzy region surrounding the Orion Nebula, is one of the nearest active star-forming regions, approximately 1,300 light-years away, and it contains multiple young stellar clusters and individual young stars in various stages of formation. The process by which a molecular cloud collapses to form stars, the interplay of gravity, turbulence, magnetic fields, and stellar feedback, is one of the most complex and computationally demanding problems in astrophysics. The interstellar medium, the gas and dust between the stars of the Milky Way, is not uniform but exists in several distinct phases at very different temperatures and densities. The hot ionized medium, plasma at temperatures of millions of Kelvin, fills a significant volume of the galaxy and is heated primarily by supernova explosions. The warm neutral and warm ionized phases are intermediate in temperature, hundreds to thousands of Kelvin, and occupy most of the remaining volume. The cold neutral medium, hydrogen gas at roughly 80 Kelvin, exists in dense clouds within the warm medium. And the cold molecular phase, the molecular clouds, is the densest and coldest component, where temperatures approach absolute zero and densities are sufficient for molecule formation. The interstellar medium cycles continuously between these phases through the processes of star formation, stellar evolution, and supernova feedback, and this cycling maintains the balance of conditions that allows ongoing star formation throughout the galaxy. The Milky Way contains an estimated 400 million brown dwarfs, objects intermediate in mass between the most massive planets and the least massive stars. Brown dwarfs have masses between approximately 13 and 80 times the mass of Jupiter, too massive to be planets, but not massive enough to sustain hydrogen fusion in their cores. They glow faintly in the infrared from the residual heat of their formation and from the gravitational contraction that occurs in the absence of nuclear burning, but they cool and dim over billions of years. The coolest and oldest brown dwarfs, called white dwarfs, have surface temperatures below 300 Kelvin, cooler than the surface of Venus and approaching room temperature. These dark, cool objects drift through the galaxy in vast numbers, largely invisible to optical telescopes, but detectable in deep infrared surveys. They may outnumber the stars in the Milky Way. White dwarfs, the remnants of stars like our Sun after they have exhausted their nuclear fuel, are extraordinarily common in the Milky Way. It is estimated that there are approximately 10 billion white dwarfs in the galaxy. A white dwarf is the compressed core of a former star, typically containing roughly the mass of the Sun compressed into a volume roughly the size of Earth. Their surface temperatures when newly formed are extremely high, tens of thousands of Kelvin, but they have no ongoing energy source and cool slowly over billions of years. The coolest white dwarfs in the Milky Way, those that have been cooling since the earliest epochs of the galaxy's history, have surface temperatures of approximately 3,000 to 4,000 Kelvin and provide one of the most reliable methods for estimating the age of the oldest stellar populations. These crystallized remnants of ancient suns drift silently through the galaxy in numbers exceeding the population of living stars. The Milky Way's dark matter halo, the invisible component of mass that makes up the majority of the galaxy's total mass, extends far beyond the visible disk and is thought to have a roughly spherical distribution with a radius of approximately 300,000 light-years. The total mass of the Milky Way, including its dark matter halo, is estimated at approximately 800 billion to 1 trillion solar masses, of which ordinary matter, stars, gas, and dust comprises only about 5 to 10%. The mass of the galaxy inferred from the orbital velocities of objects at large distances from the center far exceeds the mass of the visible matter, just as Vera Rubin's observations of other galaxies showed for the first time in the 1970s. The dark matter halo is the largest component of the Milky Way by mass, yet it produces no detectable light or radiation of any kind. Its existence is inferred entirely from its gravitational effects. The rotation of the Milky Way is differential. Different parts of the galaxy rotate at different speeds, and the angular velocity decreases with distance from the center. The Sun orbits the galactic center at approximately 220 kilometers per second, completing a full orbit in approximately 225 to 230 million years, a period sometimes called a galactic year or cosmic year. The last time the Sun was in its current position relative to the galactic center, the first dinosaurs were beginning to appear on Earth. One galactic year before that, complex multicellular life had just begun colonizing the land. The deep geological and biological history of Earth can be measured in fractions of a galactic year, a perspective that gives the very slow cosmic rhythms of the galaxy a tangible connection to the history of life on this planet. The spiral arms of the Milky Way are not material structures that rotate with the galaxy. They are density waves, regions of slightly enhanced density that move through the disk at a different angular speed from the stars themselves. Stars, gas, and dust pass through the spiral arms as they orbit the galactic center, spending a relatively brief time in the arm before moving on. The density wave compresses gas as it passes through, triggering the formation of new stars, which then illuminate the arm from within. The young, hot, blue stars that make the arms visible are born in the arm and die within it, their short lifetimes ensuring that they are always found near the arm pattern even though the underlying stellar population flows through. The spiral pattern is a standing wave in the density of the disk, maintained by gravitational resonances, not a fixed structure of specific stars. The globular clusters of the Milky Way are ancient spherical collections of stars, each containing tens of thousands to millions of stars tightly bound by gravity, orbiting the galaxy in the halo on long elliptical orbits that take them out to great distances and then back through the inner galaxy. Approximately 150 to 160 globular clusters have been identified in the Milky Way, though the total number is estimated at somewhat higher due to obscuration by dust and distance. The stars in globular clusters are among the oldest in the universe. Most were formed in the first few billion years after the Big Bang, before the interstellar medium had been substantially enriched with heavy elements by stellar evolution. Their ages, estimated from the properties of their evolved stars, are between 10 and 13.5 billion years, making them some of the oldest objects that can be precisely dated. Omega Centauri, the most massive globular cluster associated with the Milky Way, contains approximately 10 million stars and may be the stripped nucleus of a dwarf galaxy that was absorbed by the Milky Way billions of years ago. The stellar populations of the Milky Way are divided into three broad groups based on their chemical composition and kinematics, reflecting different epochs and environments of formation. Population 1 stars, including the Sun, are relatively metal-rich. They contain significant proportions of elements heavier than hydrogen and helium, and are found predominantly in the thin disk on roughly circular orbits. Population 2 stars are metal-poor, found predominantly in the thick disk, bulge, and halo, and on more elliptical, inclined orbits. Population 3 stars, the hypothetical first generation of stars, formed from almost pure hydrogen and helium before any stellar nucleosynthesis had enriched the interstellar medium, have never been directly observed, but their existence is inferred from theoretical models of early galaxy formation, and their deaths in early supernovae produced the first heavy elements that subsequent generations of stars incorporated. The chemical composition of stars is a record of their birth environment, encoding the history of element production in the galaxy. The Milky Way is a member of the Local Group, a gravitationally bound collection of galaxies that occupy a region approximately 10 million light-years across. The Local Group contains approximately 50 known member galaxies, including 2 large spirals, the Milky Way and Andromeda, and a large number of dwarf galaxies, many of which are satellites of the 2 large galaxies. The total mass of the Local Group is approximately 3 to 5 trillion solar masses, of which the Milky Way and Andromeda each contribute roughly comparable amounts. The Local Group is itself part of a larger structure called the Virgo supercluster, which contains approximately 100 galaxy groups and clusters, and the Virgo supercluster is part of the even larger Laniakea supercluster, a structure approximately 500 million light-years across containing roughly 100,000 galaxies. The proper motion of the Milky Way through space, its velocity relative to the rest frame of the cosmic microwave background, is approximately 600 kilometers per second in the direction of the Great Attractor, a massive concentration of galaxies and dark matter approximately 250 million light-years away in the direction of the constellations Hydra and Centaurus. The Great Attractor is not a single object, but a region of enhanced mass density that gravitationally draws the Milky Way, along with the entire Local Group, the Virgo cluster, and a broader region of the universe, toward it. The Milky Way is not simply orbiting the Virgo supercluster. It is flowing toward the Great Attractor, as part of the larger-scale streaming of matter in the universe driven by gravitational attraction to concentrations of mass. The interstellar medium of the Milky Way contains complex organic molecules that are the building blocks of biological chemistry. Radio astronomers have detected more than 200 distinct molecular species in interstellar clouds, including water, ammonia, formaldehyde, methanol, ethanol, and glycolaldehyde, a simple sugar-related molecule. Amino acid precursors have been identified in meteorites that formed from the same molecular cloud as the solar system, confirming that the interstellar chemistry that produces complex organics translates into the solid materials of planetary systems. The distribution of these molecules throughout the interstellar medium means that the chemical inventory needed for life is not rare or special to Earth, but is present throughout the galaxy, delivered to forming planetary systems as part of the ordinary chemistry of star and planet formation. The Milky Way has experienced multiple epochs of enhanced star formation triggered by galaxy interactions and mergers. Evidence from stellar age distributions, comparing the ages of stars in different populations using isochrone techniques and abundance patterns, shows bursts of star formation approximately 2 billion and 6 billion years ago, in addition to the general decline from a peak around 10 billion years ago. These bursts may correspond to close passages or mergers with satellite galaxies that compressed molecular gas and triggered enhanced star formation. The Gaia Enceladus merger, which deposited a significant stellar population into the halo approximately 10 billion years ago, is thought to have triggered one such burst in the thick disk. The ongoing interaction with the Magellanic Clouds has likely influenced star formation in the outer disk. The star formation history of the Milky Way is not a smooth decline, but an episodic story shaped by gravitational events. The thin disk of the Milky Way, where most of its ongoing star formation and most of its young and middle-aged stellar population resides, has a characteristic scale height of approximately 1,000 light-years, meaning that the density of stars decreases with an exponential scale of about 1,000 light-years above and below the midplane. The Sun sits approximately 25 to 50 light-years above the midplane of the disk, slightly above the centerline, which means that from the southern hemisphere of Earth, you are looking more directly toward the midplane of the galaxy than from the northern hemisphere, though the difference is too small to be visually significant. The disk is not perfectly smooth in its stellar distribution, but shows corrugations, wave-like variations in the disk density and midplane height that extend across thousands of light-years, thought to be driven by the passage of satellite galaxies through the disk. The most luminous stars in the Milky Way are supergiants, massive stars in the later stages of their evolution, expanding and brightening dramatically as they approach their deaths. Stars like Eta Carinae, approximately 160 solar masses, one of the most massive stars known, located approximately 7,500 light-years away in the Carina Nebula, are so luminous that they approach or exceed the theoretical Eddington limit, the point at which radiation pressure from the star's own light overcomes gravity and begins to blow material off the surface. Eta Carinae underwent a major eruption in 1843, briefly becoming the second brightest star in the sky despite its distance, and has since formed a visible bipolar nebula of ejected material around it. Such stars are short-lived on stellar timescales, massive enough to burn their fuel in mere millions of years, and their violent deaths as supernovae and potentially as long-duration gamma-ray bursts have enriched the interstellar medium with heavy elements over the history of the galaxy. The oldest stars in the Milky Way halo, sometimes called extremely metal-poor stars, because they contain almost no elements heavier than hydrogen and helium, are the closest observable relics of the conditions of the early universe. Stars like SMSS J031300.36-6708393.3, which has an iron abundance approximately 10 million times lower than the Sun and contains carbon as its primary heavy element, formed from gas that had been enriched by the nucleosynthesis of only one or a few first-generation stars. Studying the chemical abundance patterns in these ancient stars allows astronomers to infer the properties of the hypothetical first stars, their masses, their explosion energies, their nucleosynthetic yields, from the chemical fingerprints they left in the stars that formed from their remnants. These metal-poor halo stars are, in effect, fossil chemistry from the first billions of years of the galaxy's history. The gaseous halo of the Milky Way, the hot, diffuse gas extending above and below the disk, has been detected in X-ray observations and is thought to extend to distances of 50,000 to 100,000 light-years from the galactic center. This hot gas, at temperatures of 1 to 2 million Kelvin, constitutes a significant reservoir of baryonic matter associated with the Milky Way, potentially containing a mass comparable to that of all the stars in the disk. It is thought to be sustained by the energy input of supernova explosions and stellar winds in the disk, which heat gas and drive it outward. The gaseous halo plays an important role in regulating star formation in the disk. It is a reservoir from which cooled gas can rain back down onto the disk to fuel future star formation, and its heating and cooling cycles influence the long-term evolution of the galaxy's star formation rate. The Milky Way is slightly larger than average for a barred spiral galaxy. Its total stellar mass is estimated at approximately 60 billion solar masses, towards the high end of the distribution for field galaxies, though not exceptional. Its halo, including dark matter, extends to a radius of approximately 300,000 to 500,000 light-years, significantly larger than the visible stellar disk. The size and mass of the Milky Way make it one of the two dominant galaxies in the local group, the other being Andromeda, which is slightly more massive, and their mutual gravitational influence governs the dynamics of the smaller galaxies in the group. In the broader context of the universe, the Milky Way is an ordinary galaxy in an ordinary environment, and this ordinariness is part of what makes it interesting. What happens here, in this unremarkable galaxy, is probably representative of what happens in a significant fraction of the universe's galaxy population. The Sagittarius Dwarf Galaxy, a satellite galaxy of the Milky Way distinct from the Magellanic Clouds, is currently being disrupted and absorbed by the Milky Way's gravitational tidal forces. Its stars have been stretched into a long tidal stream that wraps approximately 3 times around the Milky Way, distributing Sagittarius stars through the halo in a pattern detected by the Sloan Digital Sky Survey in the early 2000s. The Sagittarius stream stars have distinctive chemical abundances, different from those of the Milky Way's indigenous halo stars, that allow them to be identified and traced. The ongoing assimilation of the Sagittarius dwarf illustrates in real time the process of galactic cannibalism by which the Milky Way has grown over billions of years, incorporating smaller satellite galaxies into its ever-growing mass. The star formation in the Milky Way's spiral arms is a self-propagating process in some regions. When a massive star forms and eventually explodes as a supernova, the shockwave from the explosion compresses nearby gas clouds, triggering the formation of new stars in adjacent regions. These new stars include massive stars that will themselves eventually explode, triggering further star formation in their neighborhoods. This self-propagating star formation creates chains and complexes of young stellar clusters and active star-forming regions strung along the spiral arms, each cluster seeding the next. The result is the structured pattern of young stellar associations, open clusters, and H2 regions, clouds of ionized hydrogen lit by young hot stars that make the spiral arms visible and define their character. The open clusters of the Milky Way, loose groupings of young stars formed from the same molecular cloud, provide snapshots of star formation at specific times and places in the galaxy's history. Unlike globular clusters, which are ancient and tightly bound, open clusters are young, loosely bound, and gradually disperse as their member stars drift apart on slightly different orbits over millions to hundreds of millions of years. Clusters like the Pleiades, approximately 440 light-years away, approximately 115 million years old, are visible to the naked eye as a compact group of blue-white stars. The Hyades, approximately 150 light-years away, approximately 625 million years old, is one of the nearest clusters and provides a crucial rung on the cosmic distance ladder. Over timescales of billions of years, the Sun's own siblings, the stars that formed from the same molecular cloud as the Sun approximately 4.6 billion years ago, have long since dispersed through the galaxy, indistinguishable from the general stellar population. The Milky Way emits radiation across the entire electromagnetic spectrum. The visible stars and their thermal emission dominate in optical wavelengths. The hot interstellar gas in the halo emits X-rays. The relativistic electrons in the galactic magnetic field produce synchrotron radiation in radio wavelengths. Molecular clouds absorb optical and emit infrared radiation. The warm dust in the disk glows in the mid-infrared. The cosmic microwave background, the oldest light in the universe, permeates the galaxy and provides the background against which all these emissions are superimposed. The Fermi bubbles emit gamma rays. Sagittarius A star produces a broad spectrum from radio through X-ray. No single wavelength gives a complete picture of the galaxy. Each band reveals a different component, a different population, a different process. Our full understanding of the Milky Way comes from combining observations across all accessible wavelengths. The Gaia mission of the European Space Agency, launched in 2013, made its science observations from July 2014 to January 15, 2025, and has revolutionized our knowledge of the Milky Way. Gaia collected more than 3 trillion observations of around 2 billion stars and other objects, measuring positions, parallaxes, proper motions, brightness, temperature, and composition with unprecedented precision. Its data releases have enabled the 3-dimensional mapping of the galaxy's stellar structure, the identification of stellar streams from disrupted satellite galaxies, the discovery of previously unknown stellar populations, the characterization of the galactic warp and its rotation, and the detailed chemical mapping of the solar neighborhood. Gaia data has confirmed that the Milky Way is more dynamic and disturbed than older static models suggested, revealed the detailed history of the galaxy's mergers through the kinematics of halo stars, and provided the most precise measurements of stellar distances and velocities ever obtained. The galaxy as it is understood today is, more than ever before, the galaxy as Gaia has shown it. The local bubble is a region of low density, hot plasma in the interstellar medium surrounding the solar system, extending approximately 300 to 500 light-years in most directions. The solar system sits within this bubble, which was likely created by a series of supernova explosions in the local stellar neighborhood over the past few million years, perhaps 10 to 20 supernovae that collectively heated and evacuated the surrounding interstellar gas. The edges of the local bubble are delineated by shells of cold, dense gas, and dust. A 2022 study used 3-dimensional dust mapping to reconstruct the 3-dimensional structure of star-forming molecular clouds in the local galactic neighborhood and found that many of the nearest and most active star-forming regions, including the Ophiuchus, Perseus, and Taurus clouds, are distributed on the surface of the local bubble, suggesting that the expanding shell of the bubble has swept up and compressed gas into these star-forming configurations. The Sun, and the Earth within it, are living inside the aftermath of ancient supernovae. The proper motions of stars, their apparent movement across the sky due to their actual transverse velocities, were first measured systematically in the 18th century by Edmund Halley, who noticed that several bright stars had moved from the positions recorded by ancient Greek astronomers. The angular motions of stars are extraordinarily small. The fastest moving nearby star, Barnard's star, moves approximately 10 arcseconds per year, and the detection of these motions over historical timescales requires precise positional measurements. With the Gaia mission, proper motions have been measured for over 1 billion stars across the galaxy, allowing the reconstruction of orbital histories, the identification of stars with unusual kinematic signatures indicating formation in different environments, and the tracing of the large-scale flow of stellar material through the disk and halo. The Milky Way in motion, not as a static structure but as a dynamical system of orbiting stars, is now a subject of detailed observational study. The structure of the inner galactic disk within a few thousand light-years of the Sun contains remarkable detail that nearby surveys have begun to characterize. The thin disk shows vertical corrugations, oscillations in the position of the disk midplane, that extend over thousands of light-years and have an amplitude of hundreds of light-years. These corrugations have been interpreted as the response of the disk to an external perturbation, likely the passage of a satellite galaxy through the disk several 100 million years ago, that set the disk oscillating in the vertical direction. Stars in the corrugation move coherently up and down as part of the oscillation, and the resulting vertical velocity patterns have been detected in large stellar surveys. The galactic disk is not a smooth, static structure, but a dynamic sheet that ripples on timescales of hundreds of millions of years. The magnetic field of the Milky Way permeates the interstellar medium and plays an important role in regulating star formation, channeling cosmic rays, and shaping the structure of the interstellar medium. The large-scale magnetic field is roughly parallel to the galactic plane and follows the spiral arm pattern, with a typical field strength of a few microgauss, extraordinarily weak by everyday standards, but significant on the scale of the galaxy. The field is generated and maintained by a galactic dynamo process, the combination of differential rotation and turbulent convection in the conducting plasma of the disk. The magnetic field prevents cosmic rays, charged particles accelerated by supernovae and other energetic processes, from streaming freely out of the galaxy. Instead, the cosmic rays spiral along magnetic field lines and are confined within the disk for millions of years before gradually diffusing out into the halo. This confinement has significant effects on the energy density of the interstellar medium and on the pressure balance that regulates star formation. The cosmic ray population in the Milky Way, the flux of energetic charged particles primarily produced by supernova shockwaves and other energetic processes, has a significant energy density comparable to that of the galactic magnetic field, the thermal pressure of the warm interstellar medium, and the turbulent pressure of the gas. These energy components are in rough equipartition, roughly equal in energy density, a configuration that suggests they are dynamically coupled and that each component regulates the others. The energy injected into cosmic rays by supernovae drives galactic winds, outflows of gas from the disk into the halo that regulate the amount of gas available for star formation and redistribute metals and energy throughout the galaxy. Understanding the cosmic ray population and its coupling to the magnetic field and gas dynamics is essential for understanding the overall energy balance and evolution of the Milky Way. Pulsars, rapidly rotating neutron stars that emit beams of radio waves, are distributed throughout the Milky Way and serve as extraordinarily precise clocks that probe the interstellar medium through which their signals travel. The dispersion of pulsar signals, the frequency-dependent delay caused by free electrons in the interstellar medium, provides information about the electron density distribution along the line of sight, allowing the construction of a three-dimensional map of the electron density of the interstellar medium. The scattering of pulsar signals by density inhomogeneities in the interstellar medium provides information about turbulence. The rotation measure of polarized pulsar signals probes the magnetic field along the line of sight. Pulsar timing arrays, networks of pulsars monitored precisely enough to detect the tiny irregularities in their pulse arrival times, are sensitive enough to detect the gravitational wave background produced by the population of merging supermassive black hole binaries in the universe, making pulsars not only probes of the Milky Way, but instruments of fundamental physics. The night sky as seen from Earth is not a complete view of the Milky Way. Dust in the disk, tiny silicate and carbonaceous grains in the interstellar medium, absorbs optical light, making many regions of the galaxy opaque at visible wavelengths. The galactic center, a region of extraordinary stellar density and astrophysical activity, is completely invisible to optical telescopes because of the approximately 27 kiloparsecs of dust-laden disk lying between us and it. Infrared and radio waves, which penetrate dust far more effectively, have provided our best views of the galactic center and the structure of the inner galaxy. The entire picture of the Milky Way that astronomers have constructed, the mapping of the spiral arm structure, the measurement of stellar populations across the disk, the characterization of the central bulge, has required careful use of wavelengths that can penetrate the dust. The optical sky is beautiful but deceptive. It shows a biased, dust-filtered view of a much richer structure. The distance from the solar system to the center of the Milky Way, approximately 26,000 light-years, or about 8,000 parsecs, was not accurately known until the 20th century. Early estimates based on the apparent distribution of globular clusters, made by Harlow Shapley in 1918, gave a distance of roughly 50,000 light-years, too large, but the first demonstration that the Sun was not near the center of the galaxy, overturning the assumption implicit in earlier models that our position was central. Modern measurements using a variety of methods, maser sources in star-forming regions, the orbits of stars around Sagittarius A star, Cepheid variable stars, and the kinematics of stars in the disk, have converged on a value of approximately 26,000 light-years, with uncertainties of less than 1,000 light-years. The distance to the galactic center is one of the fundamental calibrations of the scale of our galaxy and of the distance measurements that extend outward from it. The solar system completes one orbit of the galactic center approximately every 225 to 230 million years, and in the approximately 4.6 billion years since the formation of the solar system, it has completed roughly 20 galactic orbits. During each of these orbits, the solar system has passed through the spiral arms of the galaxy multiple times, because the spiral pattern rotates at a different angular speed from the stars. The Sun passes through each arm approximately every few hundred million years. These passages through the denser regions of the arms, with their higher concentrations of molecular gas and young, massive stars, may have influenced Earth's geological and biological history through variations in the cosmic ray flux, potential perturbations to the Oort cloud, and the consequent variation in the flux of comets into the inner solar system, and possibly through climate effects mediated by changes in cloud formation. The connection between galactic dynamics and Earth history is an active area of speculative research with some intriguing but not yet definitive correlations. The Milky Way's spiral arms are not empty between the stars. The space between stellar systems is filled with the interstellar medium, a dilute but chemically rich mixture of gas and dust that represents the raw material from which new stars and planets will form. The average density of the interstellar medium in the disk is roughly 1 atom per cubic centimeter, an extraordinarily dilute medium by any laboratory standard, but one that, integrated across the vast volume of the disk, represents an enormous total mass of material. The gas is primarily hydrogen, in various forms. Neutral atomic hydrogen, which is detectable in radio wavelengths at 21 centimeters. Ionized hydrogen, which glows in visible light in the regions around hot young stars. And molecular hydrogen, the dominant form in the cold, dense clouds where star formation occurs. Each form traces a different aspect of the galaxy's thermal and dynamical structure. The 21-centimeter hydrogen line, the radio emission produced when the electron in a neutral hydrogen atom flips from a slightly higher energy spin state to a slightly lower one, has been one of the most important tools in mapping the structure of the Milky Way. Because radio waves penetrate the dust that blocks optical observations, the 21-centimeter line can be detected from hydrogen clouds anywhere in the galaxy, not just in the relatively unobscured regions accessible to optical telescopes. The velocity of the emitting hydrogen along the line of sight is encoded in the Doppler shift of the emission line, and combined with a model of galactic rotation, this velocity information allows the approximate distance to the hydrogen to be estimated. The surveys of 21-centimeter emission that began in the 1950s provided the first comprehensive maps of the large-scale gas distribution in the Milky Way disk, revealing the spiral arm pattern for the first time. The chemical enrichment of the Milky Way over its history can be traced through the abundance of heavy elements, all elements heavier than hydrogen and helium, in stars of different ages. The oldest stars in the galaxy have very low abundances of heavy elements, reflecting the almost primordial composition of the gas from which they formed. Successively younger generations of stars show progressively higher heavy element abundances, as each generation of dying stars enriches the interstellar medium with the products of nucleosynthesis. The slope of this relationship, the rate at which heavy element abundance increases with decreasing stellar age, varies in different parts of the galaxy, reflecting the different star formation histories of different components. The bulge enriched rapidly in the early galaxy. The thin disk enriched more gradually. The outer disk, where star formation has always been lower, shows lower heavy element abundances even in relatively young stars. The chemical gradient across the disk, inner regions more metal-rich than outer, is a direct record of the radial variation in star formation history. The Milky Way's central molecular zone, the region within approximately 1,000 light-years of the galactic center, is one of the most extraordinary environments in the galaxy. The gas density is approximately 100 times higher than in the spiral arms. The temperatures are higher. The turbulent velocities of the gas are far greater. The magnetic field is roughly 100 times stronger than in the local interstellar medium. The cosmic ray density is higher. The tidal forces from the central mass are strong enough to disrupt molecular clouds that would be gravitationally stable anywhere else in the galaxy, preventing ordinary star formation. And yet star formation does occur in the central molecular zone, in massive, dense clumps, like the Sagittarius B2 cloud, one of the largest molecular clouds in the galaxy, containing the largest known concentrations of complex organic molecules that somehow overcome the disrupting tidal forces to form stars in an environment utterly unlike the spiral arm regions where most of the galaxy's star formation occurs. The circumnuclear disk, a ring of gas and dust approximately 2 to 7 light-years from Sagittarius A star, orbits the central black hole at approximately 100 kilometers per second and represents the innermost gas reservoir in the galaxy. The disk is clumpy, asymmetric, and heavily irradiated by the strong UV and X-ray emission from the galactic center. At even smaller radii, within the central parsec, dense streamers of gas called mini-spirals orbit Sagittarius A star and hot young stars, the S stars whose orbits have been tracked to measure the black hole's mass, move on highly eccentric orbits that bring them within the gravitational sphere of influence of the black hole. The presence of these young massive stars so close to the black hole, in a region where tidal forces should prevent the formation of stars from ordinary molecular gas clouds, is one of the more puzzling features of the galactic center and has been called the paradox of youth. The pulsar population of the Milky Way provides a census of the neutron star remnants of massive stars that have ended their lives in supernova explosions throughout the history of the disk. Approximately 3,000 pulsars have been detected in the Milky Way, but this is thought to be a small fraction of the total population. The majority are too distant, too faint, or beaming in directions that do not intersect the Earth to be detected. Models of the pulsar population suggest there may be approximately 100,000 active pulsars in the galaxy. Neutron stars that are no longer active pulsars, those whose emission beams have slowed and dimmed over millions of years, number far more, perhaps 1 billion. Together with the estimated 10 billion white dwarfs, the Milky Way contains more stellar remnants than active stars, a reflection of the billions of years of stellar evolution that have already occurred since the galaxy's formation. The gas dynamics of the galactic disk are driven by a complex interplay of gravity, pressure, magnetic forces, and the energy inputs from stars. Supernovae inject kinetic energy into the interstellar medium through their expanding shock waves, driving turbulence that resists the gravitational collapse of gas into stars on galactic scales. The radiation pressure from young hot stars ionizes and heats gas in their vicinity, disrupting the molecular clouds from which they formed. Stellar winds from massive stars and asymptotic giant branch stars return processed material to the interstellar medium. The combined effect of all these feedback mechanisms, star formation feedback, regulates the rate of star formation by making it self-limiting. When star formation increases, feedback increases, which heats and disperses gas, which reduces star formation. This self-regulation has maintained a roughly constant star formation rate in the Milky Way disk for billions of years, despite the galaxy's evolution. The Milky Way's satellite galaxy population provides important constraints on the nature of dark matter. The standard model of cosmology, lambda cold dark matter, predicts that large galaxies should have hundreds to thousands of satellite galaxies, based on the hierarchical merging of dark matter halos. The observed number of satellite galaxies of the Milky Way is much smaller, approximately 60 known satellites at the time of writing. This discrepancy, sometimes called the missing satellites problem, has generated extensive theoretical work. Possible resolutions include the idea that most of the predicted small dark matter halos did not form stars and are therefore invisible, the suppression of galaxy formation in small halos by UV background radiation after reionization, the tidal stripping and disruption of satellites by the Milky Way's gravity, and the possibility that dark matter behaves differently from the cold, collisionless particle assumed in the standard model. The satellite galaxy population of the Milky Way is one of the most important testing grounds for theories of dark matter and galaxy formation on small scales. The Milky Way's disk has a characteristic scale length, the radial distance over which the surface density of stars decreases by a factor of E, of approximately 3 kiloparsecs, or roughly 10,000 light-years. Beyond this scale length, the stellar density decreases exponentially with increasing galactocentric radius. The outer disk, beyond approximately 15 to 20 kiloparsecs from the center, contains relatively few stars and is sparse and irregular, with a low surface density that makes it difficult to characterize. Recent wide-field surveys have detected an excess of stars in the outer disk, sometimes called the Monoceros ring, that may represent the disrupted debris of an accreted dwarf galaxy or a ring-like overdensity created by gravitational perturbations. The structure of the outer disk is one of the less well-characterized aspects of the Milky Way's morphology. The Milky Way in infrared light looks different from the Milky Way in optical light. At optical wavelengths, the disk is interrupted by dark patches of obscuring dust, and the galaxy is dominated by the light of intermediate age and old stars combined with the luminous blue stars of the spiral arms. In the near-infrared, the dust becomes more transparent, and the old stellar population of the bulge and thick disk becomes more prominent. The galaxy appears more symmetric, more obviously barred, and the central bulge stands out clearly. In the mid-infrared, warm dust emission reveals the locations of star-forming regions and planetary nebulae. In the far infrared, cold dust emission traces molecular clouds. The infrared Milky Way, particularly as revealed by missions like Spitzer and WISE, has provided the most complete and least dust-biased maps of the galaxy's stellar mass distribution and has been essential for characterizing the three-dimensional structure of the bar and bulge. The Milky Way's gas disk extends considerably further than its stellar disk. Neutral hydrogen traced by 21 cm emission has been detected at galactocentric radii exceeding 60 kiloparsecs, roughly twice the extent of the stellar disk. This extended gas disk, warped and irregular at large radii, represents infalling material from the cosmic web and the circumgalactic medium that is gradually accreting onto the galaxy, as well as gas that has been driven outward by feedback processes. The total mass of neutral hydrogen in the Milky Way is approximately 5 to 10 billion solar masses, substantially less than the stellar mass, but representing a reservoir of future fuel for star formation. Understanding how this gas reservoir is replenished through accretion from the circumgalactic medium and how it is consumed through star formation and driven away by feedback is central to understanding how the galaxy will evolve in the future. The stellar kinematics of the Milky Way, the distribution of stellar velocities, contain a record of the galaxy's dynamical history. Stars formed in the disk gradually gain kinetic energy over time through gravitational scattering by molecular clouds, passing spiral arms, and other inhomogeneities in the disk potential, a process called disk heating. Young stars have low velocity dispersions and move in nearly circular orbits close to the disk midplane. Old stars have higher velocity dispersions and more inclined orbits, distributed in a thicker layer. This age-velocity dispersion relation has been measured in the solar neighborhood and provides information about the rate of disk heating over the history of the galaxy. Kinematic substructure, groups of stars with correlated velocities that do not fit the smooth background, records the imprints of past dynamical events including satellite galaxy passages, resonances with the bar and spiral arms, and the dispersal of star-forming associations. The galactic bar of the Milky Way has important dynamical effects on the orbits of stars and gas in the inner galaxy. Stars near the bar can be captured into resonant orbits, orbits where the orbital frequency of the star is in a simple ratio to the rotation frequency of the bar, causing the star to feel a persistent gravitational perturbation from the bar. These resonant orbits create a zoo of complex orbital families, elongated orbits along the bar, loop orbits, chaotic orbits, that populate the bar itself and give it its elongated shape. The bar also drives gas inward along its length toward the galactic center, potentially contributing to the gas supply of the central star-forming regions. The corotation resonance, where stars orbit at the same angular speed as the bar, and the outer Lindblad resonance, where the orbital epicyclic frequency matches the bar's rotation. are particularly important dynamical features that influence the distribution of stars and gas in the inner galaxy. Looking from far outside the Milky Way, from a position in the local group, far enough away to see the whole galaxy at once, the Milky Way would appear as a flattened, luminous disk with a bright central bar and 2 to 4 visible spiral arms wound outward from the ends of the bar. The disk would show a slight warp in its outer regions. The central bulge would glow with the combined light of billions of old stars. On one side of the disk, the Fermi bubbles would be visible at gamma-ray wavelengths as 2 enormous lobes extending far above and below the plane. 2 small, irregular companion galaxies, the Magellanic Clouds, would be visible nearby, connected to the main galaxy by a faint gaseous stream. Scattered around the disk and extending into a large spherical halo would be the dots of light from approximately 150 globular clusters, each a dense ball of ancient stars orbiting the galaxy in long elliptical paths. The name Milky Way comes from the ancient appearance of the galaxy itself, a pale, milk-white band across the night. In Greek myth, it was connected with spilled milk from the goddess Hera. In many other cultures, the band had different meanings: a road of souls, a river in the sky, a path used by spirits, animals, ancestors, or gods. Long before it was understood as a galaxy, it was recognized as something special, not a constellation, not a single star, but a continuous luminous structure that seemed to divide the heavens. The scientific understanding came much later. Galileo, using one of the first telescopes in the early 17th century, resolved parts of the Milky Way into countless faint stars. The river of light was not missed. It was stars too numerous and too distant for the unaided eye to separate. That discovery changed the scale of the human universe. Before telescopes, the Milky Way was a visible mystery. After telescopes, it became evidence that the night sky contained far more stars than human eyes could count. But even then, the true nature of the Milky Way remained hidden. For centuries, astronomers debated whether the Milky Way was the whole universe or only one star system among others. The answer required measuring distances on scales that seemed almost impossible. The stars did not reveal their distances easily. They looked fixed, as if pinned to a celestial sphere. Only with careful parallax measurements, variable stars, star counts, and eventually the recognition of other galaxies did the Milky Way become what it is now. Not the universe itself, but one galaxy among a vast population of galaxies. Parallax is one of the simplest and most powerful ideas in astronomy. If you hold up a finger and look at it first with one eye and then the other, it appears to shift against the background. Nearby stars do the same thing as Earth moves from one side of its orbit to the other, though the shift is incredibly small. Measuring that tiny annual shift allows astronomers to calculate distance directly. The first successful stellar parallax measurement was made in 1838 by Friedrich Bessel for the star 61 Cygni. Its apparent shift was less than 1/3 of an arcsecond, an angle so small that it is difficult to imagine, yet it opened the first reliable distance scale beyond the solar system. Every modern map of the Milky Way ultimately rests on this principle: the patient measurement of tiny stellar motions against the background of space. The difficulty of mapping the Milky Way is that distance changes everything. A bright star may be nearby and modest, or far away and intrinsically enormous. A faint star may be small and close, or gigantic and buried behind dust. Without distance, the sky is a flat illusion. With distance, it becomes architecture. The Gaia mission has turned that architecture from a sketch into something close to a living three-dimensional atlas. By measuring the positions and motions of stars with extraordinary precision, Gaia has shown that the Milky Way is not a smooth disk, but a layered, warped, rippling, breathing structure. Stars do not simply sit in place. They stream, drift, oscillate, migrate, and carry the memory of every gravitational disturbance that has passed through the galaxy. One of the most important ideas in modern galactic astronomy is that stars are fossils, not in the biological sense, but in the chemical sense. A star preserves the composition of the gas cloud from which it formed. If that cloud had been enriched by many previous generations of stars, the new star will contain more heavy elements. If it formed early, from gas almost untouched by stellar death, it will contain very little beyond hydrogen and helium. Astronomers call all elements heavier than helium metals, even oxygen, carbon, neon, and iron. A metal-rich star is therefore a star born from gas that had already been processed by earlier stars. The Sun is metal-rich enough to build rocky planets, oceans, geology, and biology. In its chemistry, it carries the debris of older stars that lived and died before the solar system existed. This means the Milky Way has a memory written in abundance patterns. Stars in the halo have different chemical fingerprints from stars in the disk. Stars born in dwarf galaxies and later absorbed by the Milky Way often carry chemical ratios that reveal their origin. Some have less iron relative to certain alpha elements. Some move on strange orbits that no ordinary disk star would have. By combining motion with chemistry, astronomers can perform what is sometimes called galactic archaeology, reconstructing the past of the Milky Way from the stars that remain. The galaxy does not keep written records, but it keeps chemical ones. Every star is a sealed sample of an ancient cloud. The Sun itself is not exactly where it was born. Stars in the galactic disk can migrate over time, shifting inward or outward from their original birth radius through gravitational interactions with spiral arms, molecular clouds, and the bar. The Sun may have formed several thousand light-years closer to the galactic center than it is today, though the exact birth location is not known. Its sibling stars, those that formed in the same original cluster from the same molecular cloud, have long since dispersed. Somewhere in the Milky Way, other stars carry almost the same chemical signature as the Sun, born beside it 4.6 billion years ago before the cluster dissolved into the general flow of the disk. Finding those lost solar siblings is difficult because a few billion years of galactic motion have scattered them across enormous distances. The Sun's path around the galaxy is not a perfect circle. It moves roughly around the galactic center, but it also oscillates up and down through the plane of the disk, like a bead moving along a wavy track. This vertical motion takes the solar system above and below the dense midplane over tens of millions of years. At the same time, the Sun's orbit is affected by the gravitational pull of spiral arms, nearby molecular clouds, and the changing structure of the galactic disk. The solar system is not fixed in a quiet room. It is moving through a dynamic gravitational environment, surrounded by stars that shift position slowly over millions of years. The night sky we see now is temporary. In a few 100,000 years, familiar constellations will have stretched and changed beyond recognition. The stars of the Milky Way do not all travel together like points painted on a rotating wheel. Each star has its own orbit, speed, inclination, and history. Some stars move calmly in the disk, circling with the general rotation. Others plunge through the halo on long elliptical paths. Some move backward relative to the disk, evidence that they may have been captured from smaller galaxies. A few stars are hypervelocity stars, moving so fast that they may eventually escape the Milky Way entirely. Some of these are thought to have been flung outward by interactions with Sagittarius A star, when a binary star system passed too close to the central black hole, and one star was captured while the other was ejected at tremendous speed. The galaxy is full of stellar motions that reveal invisible gravitational encounters. The Oort cloud, the distant spherical reservoir of icy bodies surrounding the solar system, is part of the connection between the Milky Way and Earth. It lies far beyond the planets, perhaps extending tens of thousands of astronomical units from the Sun. At those distances, the Sun's gravitational hold is weak enough that the wider galactic environment matters. The tide of the Milky Way, the gravitational pull of the galactic disk and passing stars, can gently disturb Oort cloud objects, nudging some inward toward the inner solar system, where they become long-period comets. In this sense, the galaxy can reach into the outskirts of the solar system. A comet seen near Earth may have begun its journey because of a tiny gravitational shift caused by the Milky Way itself. The solar system is currently moving through a region of interstellar gas called the local interstellar cloud, a warm and partially ionized cloud inside the larger local bubble. The heliosphere, the vast bubble blown by the solar wind around the Sun, pushes against this interstellar material as the solar system travels through it. The boundary where the solar wind yields to interstellar space is called the heliopause. Voyager 1 and Voyager 2 have crossed this boundary, becoming the first human-made objects to enter interstellar space. They did not leave the solar system in the gravitational sense, because they are still far inside the Oort cloud, but they did leave the protective plasma environment of the Sun. They are now moving through the thin material between the stars of the Milky Way. The local bubble is a reminder that our region of the galaxy was shaped by stellar violence. Supernovae exploded near the Sun's current neighborhood in the past few million years, sweeping hot gas outward and carving a cavity in the interstellar medium. The solar system now drifts inside that cavity. Around its edges, compressed shells of gas have formed nearby star-forming regions. This means the calm sky above Earth is not a sign of a static environment. It is the aftermath of ancient explosions. The space around us was cleared, heated, and structured by massive stars that lived quickly and died long before human beings existed. The quietness of our present neighborhood is partly the quiet after supernovae. Supernovae are among the most important engines in the Milky Way. They create and distribute many of the elements that make planets and life possible. Massive stars forge elements up to iron in their cores. In the explosion and in the extreme conditions around it, heavier elements are formed and scattered into space. The shockwaves compress gas, trigger new star formation, heat the interstellar medium, and inject cosmic rays into the galaxy. Without supernovae, the Milky Way would be chemically poorer, less dynamic, and less capable of making rocky worlds. The calcium in bones, the iron in blood, and the silicon in Earth's crust all belong to a long galactic chain of stellar birth and death. The Crab Nebula is one of the most famous supernova remnants in the Milky Way. In the year 1054, astronomers in China and elsewhere recorded a new star bright enough to be visible in daylight. Today, the expanding debris from that explosion forms a luminous nebula in the constellation Taurus, powered from within by a rapidly rotating neutron star called the Crab Pulsar. The pulsar spins about 30 times per second, releasing beams of radiation and energizing the surrounding gas. The Crab Nebula is not only beautiful, it is a laboratory for high-energy astrophysics. It shows what remains when a massive star dies and its core collapses into one of the densest objects in the universe. Neutron stars are scattered throughout the Milky Way in enormous numbers. They are the collapsed cores of massive stars, with masses greater than the Sun compressed into spheres only about 20 kilometers across. A teaspoon of neutron star matter would have a mass comparable to a mountain if it could exist outside the star. Some neutron stars become pulsars, their beams sweeping across Earth like lighthouse signals. Others become magnetars, with magnetic fields so intense that they reshape atoms and produce enormous bursts of X-rays and gamma rays. These objects are rare in the visible sky, but common in the hidden inventory of the galaxy. The Milky Way is filled not only with shining stars, but with the compact remnants of stars that have already ended. Black holes also drift through the Milky Way, not only at the center but throughout the disk and halo. Stellar mass black holes form when massive stars collapse at the end of their lives. Most are invisible unless they are feeding on a companion star or interacting with surrounding material. There may be tens of millions of stellar mass black holes in the Milky Way, wandering silently through the galaxy. A black hole does not announce itself unless matter falls in or its gravity bends light in a measurable way. Some are found in X-ray binaries, where gas pulled from a companion star forms a hot accretion disk. Others may be detected through gravitational microlensing, when their gravity briefly magnifies a background star as they pass in front of it. The galaxy contains many dark objects whose presence is known only by what they do to light and motion. Gravitational microlensing has opened a strange window into objects that would otherwise be invisible. When a star, brown dwarf, black hole, or free-floating planet passes between Earth and a more distant star, its gravity bends and magnifies the background light. The foreground object may emit no light of its own, but for a brief period, the background star brightens in a characteristic way. Surveys toward the crowded bulge of the Milky Way have used microlensing to detect planets orbiting distant stars and possible rogue planets drifting without a star. These events are rare and brief, but they reveal that the galaxy contains not only stars and planets in familiar systems, but also lonely worlds moving through interstellar space in darkness. Rogue planets may be common in the Milky Way. Some form directly from collapsing gas, like tiny failed stars. Others are ejected from planetary systems during the chaotic early stages of planet formation, when young planets scatter each other gravitationally. A rogue planet does not orbit a star. It moves through the galaxy alone, dark at the surface, warmed only by internal heat, radioactive decay, and possibly tidal or residual formation energy. If it has a thick atmosphere or a subsurface ocean, it might remain geologically or chemically active for long periods. These worlds are among the quietest members of the galaxy, planets without sunsets, without seasons from a parent star, without daylight at all, yet they may be present in numbers comparable to stars or even greater. The planets discovered around other stars have changed the way the Milky Way is understood. Before the 1990s, no planet had been confirmed around a sun-like star beyond the solar system. Now, thousands of exoplanets are known, and statistical studies suggest that planets are common throughout the galaxy. Many stars have planets. Many have multiple planets. Some planets orbit close enough to their stars that their years last only a few days. Some are larger than Jupiter and hotter than molten metal. Some are rocky worlds in or near habitable zones where liquid water could exist on the surface under the right atmospheric conditions. The Milky Way is not merely a galaxy of stars. It is a galaxy of planetary systems. Red dwarf stars are the most common stars in the Milky Way. They are small, cool, faint, and long-lived, burning their hydrogen so slowly that their lifetimes can exceed hundreds of billions or even trillions of years, far longer than the current age of the universe. Because they are faint, they are difficult to see at large distances, yet they dominate the stellar population by number. Many have planets. Some have rocky planets in close orbits where temperatures may allow liquid water. But red dwarf planets face challenges: tidal locking, stellar flares, atmospheric erosion, and high-energy radiation during the star's active youth. Whether red dwarf systems are good homes for life is one of the most important questions in astrobiology, because if they are, then potentially habitable worlds may be extremely common in the Milky Way. The idea of a galactic habitable zone is an attempt to describe where in a galaxy complex life might be most likely. Too close to the galactic center, stellar density is high, supernova rates are higher, and radiation environments may be more dangerous. Too far out in the disk, heavy elements may be too scarce to form many rocky planets. Somewhere between these extremes, a region may exist where metallicity is high enough for planets and hazards are moderate enough for long-term biological stability. The Sun appears to lie in such a relatively favorable region, though the idea remains debated. Life does not require a perfect location, but it does require time. Earth needed billions of years for complex life to arise. A quiet galactic environment may be one of the hidden conditions that made that possible. The Milky Way is full of nebulae that are not just beautiful clouds, but active physical systems. The Orion Nebula is a stellar nursery where young stars are sculpting the gas from which they were born. The Eagle Nebula contains the famous pillars of creation, dense columns of gas and dust eroded by radiation from nearby young stars. The Carina Nebula contains some of the most massive stars in the galaxy, including Eta Carinae, whose eruptions have shaped surrounding gas into complex structures. These nebulae are transitional objects. They are the raw material of future stars, the illuminated leftovers of star formation, and the sculpted surfaces where radiation, gravity, turbulence, and magnetic fields compete. Looking at a nebula is looking at the galaxy in the act of making itself. Dust is one of the most important and easily underestimated components of the Milky Way. Interstellar dust grains are tiny, often smaller than the wavelength of visible light, made of silicates, carbon compounds, ices, and complex organic coatings. They are only a small fraction of the galaxy's mass, but they shape what we can see. Dust absorbs and scatters visible light, creating dark lanes through the Milky Way and hiding large parts of the inner galaxy. It also provides surfaces on which molecules form, including molecular hydrogen, the basic fuel of star formation. Dust grains are born in the cool outer atmospheres of dying stars and in supernova ejecta, then travel into interstellar clouds where they become part of the next generation of stars and planets. The dust that blocks starlight is also the dust that helps build worlds. Some of the darkest features in the Milky Way are dark nebulae, clouds of dust and cold gas seen not because they shine, but because they hide the light behind them. To the unaided eye, they may appear as black gaps in the Milky Way star fields. In cultures of the Southern Hemisphere, especially among indigenous Australian traditions and South American traditions, some constellations were identified not by bright stars, but by these dark shapes, including the Great Emu in the sky, formed by dark nebulae against the Milky Way. Scientifically, these dark clouds are often places where future stars may form. A region that looks empty in visible light may be dense with cold material, collapsing slowly towards stellar birth. Open clusters are important because they let astronomers study groups of stars with the same age and initial composition. The stars in an open cluster form together from one molecular cloud, but because they have different masses, they evolve at different speeds. Massive stars burn quickly and leave the main sequence first. Smaller stars persist longer. By studying the point at which stars of a cluster begin to evolve away from the main sequence, astronomers can estimate the cluster's age. This method, called main sequence turn-off fitting, is one of the foundations of stellar astrophysics. The cluster becomes a clock. The Pleiades, the Hyades, and many other clusters are not only visually striking. They are calibrated populations that teach us how stars age. Variable stars have also been essential to mapping the Milky Way. Cepheid variables pulsate with periods directly related to their intrinsic brightness. By measuring the period, astronomers can determine how luminous the star truly is. By comparing that true luminosity with the star's apparent brightness, they can calculate distance. This period luminosity relationship, discovered by Henrietta Swan Leavitt while studying variable stars in the Magellanic Clouds, became one of the most important tools in astronomy. It allowed the scale of the Milky Way to be measured more accurately and helped prove that the spiral nebulae were galaxies beyond our own. A star that rhythmically brightens and fades became a ruler for the universe. The Magellanic Clouds are not only satellite galaxies, they are also laboratories. The Large Magellanic Cloud contains the Tarantula Nebula, one of the most active star-forming regions in the local group. It also hosted supernova 1987A, the nearest observed supernova since the invention of modern telescopes. That explosion allowed astronomers to detect neutrinos from a stellar core collapse and to watch the expanding shockwave interact with rings of gas around the dying star. The Magellanic Clouds are close enough for individual stars and nebulae to be studied in detail, but different enough from the Milky Way in metallicity and structure to reveal how star formation changes under different galactic conditions. They are companions, future merger partners, and scientific windows into galaxy evolution. The halo of the Milky Way is not empty. It contains globular clusters, old stars, stellar streams, hot gas, dark matter, and the debris of smaller galaxies torn apart by tidal forces. Stellar streams are among the clearest evidence that the Milky Way is still assembling itself. When a dwarf galaxy or globular cluster is disrupted, its stars spread along its orbit, forming long, thin ribbons around the galaxy. These streams can wrap around the Milky Way for tens or hundreds of thousands of light years. They are not random. They trace the gravitational field through which they move, and by studying their shapes and motions, astronomers can infer the distribution of dark matter in the halo. A stream of stars is a visible line drawn through an invisible gravitational landscape. The Gaia-Enceladus merger was not the only ancient collision recorded in the Milky Way. The galaxy's halo contains multiple structures: the Helmy streams, the Sequoia event, the Kraken or Heracles population proposed in some studies, and other debris groups, each potentially representing a smaller galaxy that was absorbed long ago. The names can sound mythological, but the evidence is physical. Groups of stars moving together in unusual orbits, with chemical patterns unlike ordinary Milky Way stars. The galaxy is therefore not a single object that formed all at once. It is a composite. It is a history of accretion, disruption, mixing, and survival. Some stars above us tonight were not born in the Milky Way at all. They were born in other galaxies that no longer exist as independent systems. The missing satellites problem is one of the reasons the Milky Way matters to cosmology. Simulations of dark matter predict many small subhalos around galaxies like ours. Observations find far fewer luminous satellite galaxies than those simulations might suggest. This does not necessarily mean the dark matter model is wrong. Small halos may exist but contain no stars, because they lost gas or never formed stars efficiently after the universe was reionized. But the question remains important. The small galaxies around the Milky Way test how dark matter behaves, how gas turns into stars, and how the faintest galaxies survive. The tiny satellites of the Milky Way may hold clues about the largest unseen structure in the universe. The central black hole of the Milky Way is quiet now, but quiet does not mean inactive forever. Gas clouds, stellar winds, and disrupted objects continue to move through the central region. Occasionally, Sagittarius A star flares in X-rays and infrared light, brightening as small amounts of material heat up near the event horizon. These flares are minor compared with active galactic nuclei in other galaxies, but they show that the black hole is not dead. It is waiting in a low accretion state. If a larger supply of gas were driven inward by a merger or bar dynamics, the center of the Milky Way could become much brighter. The calm central black hole is part of a system capable of change on galactic timescales. The paradox of youth near Sagittarius A star remains one of the strangest puzzles of the galactic center. Young massive stars are found in a region where tidal forces from the black hole should make ordinary star formation extremely difficult. Gas clouds passing close to the black hole should be torn apart rather than collapse into stars. Yet young stars are there, moving rapidly around the central mass. Some theories propose that they formed farther out and migrated inward. Others suggest that an unusually dense gas disk near the black hole fragmented under its own gravity and formed stars in place. The answer matters because it tells us how star formation can occur in extreme gravitational environments, including the centers of other galaxies. The Milky Way's central region is also rich in high-energy phenomena. There are filaments visible in radio waves, long narrow structures that trace magnetic fields. There are hot plasma bubbles, supernova remnants, dense molecular clouds, and energetic particle populations. The center of the galaxy is not simply a bright bulge of stars around a black hole. It is a complicated ecosystem of gravity, gas, magnetism, radiation, and stellar death. If the solar neighborhood is a relatively quiet suburb, the central molecular zone is a crowded industrial core, dense, turbulent, magnetized, and chemically rich, where the ordinary rules of calm star formation are distorted by extreme conditions. The Milky Way contains not only individual stars, but a kind of stellar weather. Supernovae blow bubbles. Stellar winds carve cavities. Radiation from massive stars ionizes gas. Magnetic fields guide charged particles. Gas falls from the halo and rains onto the disk. Galactic fountains lift material upward from the disk after supernova heating, then allow it to cool and fall back. This circulation of gas between disk and halo helps regulate star formation over billions of years. A galaxy is not a sealed container. It breathes. Gas flows in, gas flows out. Stars form, stars die, metals are launched, and some of that enriched material returns to become future stars and planets. The future of star formation in the Milky Way depends on gas. Stars are made from cold gas, and the supply is finite unless replenished. The galaxy has already converted a large fraction of its original gas into stars or remnants. New gas can arrive from the circumgalactic medium, from satellite galaxies, and from recycled material returned by dying stars. The Magellanic Stream may eventually deliver gas to the Milky Way, helping fuel future star formation. But over very long timescales, the galaxy will form fewer and fewer new stars. Massive blue stars will disappear first because they live briefly. Red dwarfs will remain for extraordinarily long times. The future Milky Way will grow dimmer, redder, and quieter as its star-forming clouds are consumed. The collision with Andromeda will not be a catastrophe in the ordinary sense for individual stars, but it will be a transformation of identity. The two spiral disks will pass through each other, stretch, warp, and throw out tidal tails. Gas clouds will collide and compress, likely triggering bursts of star formation. The central black holes will eventually spiral together, emitting gravitational waves as they merge. After several close passages, the ordered spiral structure will dissolve into a larger, more rounded elliptical or lenticular galaxy. Future astronomers, if any exist around surviving stars, may not see a Milky Way as we know it. They may see the remnant of two great spirals blended into one system, sometimes informally called Milkomeda or Milkdromeda. The galaxy has a future as dramatic as its past. By the time the Milky Way and Andromeda merge, the Sun itself will be approaching the later stages of its life. The increasing brightness of the Sun will have profound consequences for Earth long before the Sun becomes a red giant. The oceans may eventually evaporate, and the planet's surface may become uninhabitable for complex life. The galaxy will continue, indifferent to this local ending. New stars will form elsewhere. Other planets will orbit other suns. The Milky Way story and the Earth's story overlap for a time, but they are not the same length. The galaxy existed before Earth, and in some form it will continue long after Earth is no longer the world we know. There is a useful humility in remembering that the Milky Way is both vast and ordinary. It is not the largest galaxy. It is not the smallest. It is not at the center of the universe. It is not unique in having spiral arms, a central black hole, dark matter, satellite galaxies, star-forming clouds, or ancient globular clusters. And yet ordinary does not mean uninteresting. Ordinary means representative. If a galaxy like this can produce stars like the Sun, planets like Earth, chemistry complex enough for life, and minds capable of mapping the system from within, then the ordinary universe is already astonishing. The most profound fact may not be that the Milky Way is special. It may be that it does not need to be special for something extraordinary to happen inside it. The view of the Milky Way from Earth is also changing because Earth is changing. Most people alive today cannot see the Milky Way clearly from where they live because of light pollution. The band of the galaxy, once an ordinary part of the night for almost every human culture, has become invisible over cities and many suburbs. This has scientific and psychological consequences. A sky without the Milky Way can make the universe feel smaller than it is. To see the galaxy with the naked eye is to recover scale, to understand, physically and emotionally, that the solar system is embedded in something much larger. The Milky Way is not only an object of astrophysics. It is part of the human relationship with the night. When you look toward the constellation Sagittarius on a dark summer night, you are looking toward the center of the galaxy. You cannot see Sagittarius A star directly with your eyes because dust blocks the optical light, but the direction is there. The dense star clouds, the dark lanes, the bright knots of the inner Milky Way all lie along that sight line. In the opposite direction, toward the winter constellations of Orion and Taurus, you are looking outward through the local arm, toward nearby star-forming regions and molecular clouds. The sky is not a flat decoration. Every direction is a line through the galactic structure, with different layers, distances, and histories stacked behind the stars. The Milky Way scale can be understood only through patience. Light from the galactic center takes about 26,000 years to reach Earth. Light crossing the full disk needs about 100,000 years. A radio signal sent today from Earth would not cross the galaxy until far in the future, after all present human civilizations had become ancient history. The galaxy is therefore not only large in space, but spread out in time. To observe it is to see different epochs at once. Nearby stars are seen as they were years ago. Distant nebulae are seen as they were thousands of years ago. The far side of the disk is seen through delay and dust. The Milky Way is never seen all at one moment, because light itself makes every observation a memory. And yet, despite that scale, the galaxy is also physically connected. Gravity links the center to the halo. Spiral arms organize gas. Supernovae enrich clouds that become planets. Magnetic fields thread enormous regions. Stars born in clusters disperse through the disk. Satellite galaxies fall in and become stellar streams. The carbon in living tissue, the oxygen in water, and the iron in blood are not local accidents. They are products of galactic circulation, matter formed in stars, distributed by explosions and winds, cooled into clouds, gathered into a solar system, and assembled on a planet into chemistry complicated enough to become aware of its origins. The Milky Way is therefore not only above us, it is inside us. Every atom heavier than hydrogen in the human body was made by stellar processes somewhere in a galaxy. Some came from ancient massive stars, some from dying lower mass stars, some from supernovae, some from neutron star mergers that produced heavy elements like gold and platinum. The galaxy is not just the setting for life. It is one of the causes of life. The matter that thinks about the Milky Way was made by the Milky Way or by the smaller systems that helped build it. This is not poetry. It is nucleosynthesis, stellar evolution, and chemical enrichment over cosmic time. A strong way to think about the Milky Way is as a system that turns simplicity into complexity. It begins with hydrogen, helium, gravity, and dark matter. It forms stars. Stars build heavier elements. Dying stars return those elements to space. Clouds mix them. New stars form with planets. Planets develop geology and chemistry. On at least one of them, chemistry becomes biology, and biology becomes a mind capable of reconstructing the whole sequence. The galaxy does not plan this. It does not know what it is doing. But the physical processes inside it create the possibility. A spiral galaxy is one of the universe's great engines for turning primordial matter into worlds. There is also a quiet mathematical beauty in the way the galaxy holds itself together. Every star is falling around the center, but because it has sideways motion, it does not fall in. Every gas cloud feels gravity, pressure, turbulence, and magnetic tension at once. Every spiral arm is both a visible pattern and a dynamical process. The Milky Way is not balanced because nothing happens inside it. It is balanced because countless processes happen together, pushing against one another across scales from dust grains to dark matter halos. Stability in a galaxy is not stillness. It is organized motion. This is why the Milky Way can feel almost impossible to picture. It is too large to imagine as an object and too slow to imagine as an event, yet it is both. The human mind wants a single image, a spiral seen from above, a bright center, arms curling outward. But the real galaxy is layered, moving, dusty, warped, chemically diverse, and historically complicated. It has no single surface, no edge like a planet, no fixed shape that remains unchanged. Its boundary fades gradually into a halo, into satellite streams, into hot gas, into dark matter, into the local group. A galaxy is less like a thing and more like a long gravitational weather system made of stars. And still, from Earth, it can appear as something simple, a pale band above a quiet horizon. That contrast is part of its power. The eye sees softness. The telescope sees structure. The radio dish sees hydrogen. The infrared detector sees through dust. The X-ray telescope sees hot gas. The gamma-ray telescope sees energetic bubbles. Gaia sees motion. Spectroscopy sees chemistry. No single human sense can perceive the Milky Way as it is. Only the combined work of instruments, mathematics, and imagination can assemble it. The galaxy we know is therefore both observed and reconstructed, seen directly in pieces and understood as a whole through reason. The Milky Way tonight is not the same galaxy it was when the first life appeared on Earth. It has rotated many times. It has formed and destroyed enormous numbers of stars. It has absorbed smaller galaxies. Its spiral structure has shifted. Its central black hole has likely changed in activity. Its gas supply has evolved. Its chemical abundance has increased. The sun has moved along its orbit, passing through changing stellar neighborhoods. Earth has carried life through all of that, while the galaxy around it continued its slow, enormous transformation. Life on Earth has never existed outside galactic history. It has always been moving through the Milky Way. The most interesting thing about the Milky Way may be the tension between intimacy and scale. It is unimaginably large, yet it is also home. It contains black holes, ancient mergers, dark matter, gamma-ray bubbles, stellar streams, and the debris of dead suns. But it also contains the familiar stars of winter and summer, the constellations, the light that guided travelers, the sky that early humans watched before cities, writing, agriculture, or astronomy. The same galaxy that can be measured in kiloparsecs and solar masses can also be seen as a pale band over a quiet landscape. It is both a scientific object and the oldest ceiling humanity has ever slept under. The Milky Way also has a relationship with time that is difficult to feel from Earth. Human beings usually experience time in days, seasons, years, and lifetimes. The galaxy measures change in millions and billions of years. A molecular cloud can take millions of years to collapse. A low-mass star can live for trillions. A spiral arm pattern can persist and change over hundreds of millions of years. A satellite galaxy can be stretched into a stellar stream over the length of time that separates the rise of mammals from the present. To study the Milky Way is to learn a slower language of change, one in which almost everything is moving, but almost nothing appears to move during a human life. The constellations are temporary patterns in this slow motion. The stars of Orion, for example, only appear to form a familiar human figure because of the current positions of unrelated stars at very different distances. Betelgeuse is hundreds of light years away. Rigel is farther. The belt stars are also distant and physically unrelated to the nearby stars that complete the pattern. Over tens of thousands of years, proper motion will distort Orion. Over hundreds of thousands, it will no longer resemble the shape known today. The same is true for Ursa Major, Cassiopeia, Scorpius, and every other constellation. The patterns people use to tell stories in the sky are snapshots of stellar motion, not permanent structures. Some stars pass close enough to the Sun to matter gravitationally on long timescales. Scholz's star, a faint red dwarf with a brown dwarf companion, passed through the outer Oort cloud roughly 70,000 years ago. It was never bright in the sky, but its passage was a reminder that the solar system does not sit in isolation. Future stars will also pass nearby, some close enough to disturb the outer comet reservoir. These encounters are not dramatic on human timescales, but they are part of the long gravitational weather of the galaxy. The Milky Way continually rearranges the neighborhoods of stars, bringing systems closer for a while and then carrying them apart again. The sky Earth sees at night is therefore a local moment in a galactic flow. The nearest stars are not the same stars that were nearest when the dinosaurs lived, and they will not be the same in the distant future. Proxima Centauri is currently the nearest known star to the Sun, but it will not always be. Other stars will take that place as the Sun continues its orbit. Some will pass close enough to become bright in the sky. Others will move away and fade into ordinary background points. The night sky is a record not only of where stars are, but of where they happen to be during this brief era of the Sun's journey. The Milky Way stars also differ in color, and that color is temperature made visible. Blue stars are hotter and usually more massive. They burn quickly and die young. Red stars are cooler and often much smaller, capable of surviving for extraordinary lengths of time. Yellow-white stars like the Sun occupy a middle ground. The color of the galaxy as a whole is therefore a mixture of stellar ages and stellar masses. Spiral arms glow blue because they contain young massive stars. The bulge glows warmer and yellower because it is dominated by older, cooler stars. A galaxy's color is a biography of its star formation. Blue means recent birth. Redder light means age, exhaustion, or long stability. If the Milky Way could be heard, not by human ears, but through translated data, it would not be silent. Pulsars would beat like precise clocks. Magnetars would erupt in high-energy bursts. Gas clouds would hum through radio emission. Molecular lines would mark the presence of carbon monoxide, ammonia, water vapor, and complex organics. The 21-centimeter line of hydrogen would form a vast radio map of the disk. Gravitational waves from compact object mergers would pass through invisibly. The galaxy is quiet only in ordinary human perception. In every physical channel that instruments can measure, it is active, structured, and full of signals. The stars closest to the Sun are mostly invisible without telescopes. This is one of the most important corrections to the way the night sky feels. The brightest stars are not usually the nearest. They are luminous enough to be seen across great distances. Most of the Sun's actual neighbors are small red dwarfs, too faint for the unaided eye. The local stellar neighborhood is therefore hidden from ordinary sight. What humans see as the bright night sky is biased toward rare luminous stars, while the true population of the galaxy is dominated by dim, long-lived stars that quietly outnumber the brilliant ones. The visible sky is beautiful, but it is not a fair census. Brown dwarfs deepen that hidden census. They occupy the boundary between stars and planets, and because they cool over time, the oldest ones become extremely faint. Some may have temperatures similar to those of planets. They do not shine by sustained hydrogen fusion, yet they are not planets in the ordinary sense. The Milky Way may contain hundreds of millions or more of these dim objects, scattered through the disk like fading embers from incomplete stellar birth. They remind us that nature does not always divide objects into clean categories. Between star and planet is a large population of almost stars, massive enough to glow for a time, too small to join the long nuclear life of true stars. The boundary between a large planet and a brown dwarf is also not as simple as it once seemed. Some objects classified as planets are more massive than some brown dwarfs. Some brown dwarfs form like stars from collapsing gas clouds, while some massive planets form in disks around stars. The difference is partly about mass, partly about formation history, and partly about convention. The Milky Way is full of objects that challenge human categories: failed stars, free-floating planets, compact remnants, stellar streams that are no longer galaxies, and gas clouds that are not yet stars. Astronomy often advances by discovering that the universe does not respect the clean labels human beings invent for it. The chemical complexity of the Milky Way extends into cold, dark clouds where almost nothing seems to be happening. In regions only 10 degrees above absolute zero, molecules collide slowly, stick to dust grains, react under the influence of cosmic rays, and build increasingly complex compounds. Some interstellar molecules are fragile. Others survive long enough to become part of new star systems. When a protoplanetary disk forms around a young star, it inherits chemistry from the parent cloud as well as new chemistry generated by heat, radiation, ice, and dust. The early solar system began inside such a chemical inheritance. Meteorites preserve some of it today, including amino acids and organic compounds that formed before Earth existed. Protoplanetary disks are the places where the galaxy turns dust into worlds. Around young stars, flattened rotating disks of gas and dust last for a few million years. Within them, dust grains collide and stick, becoming pebbles, then rocks, then planetesimals, then planetary embryos. Some grow into rocky planets. Some accumulate gas and become giants. Some are thrown inward, outward, or out of the system entirely by gravitational interactions. The discovery of protoplanetary disks in the Orion Nebula and elsewhere confirmed that planet formation is not a rare afterthought, but a natural part of star formation. Every new star-forming region in the Milky Way may contain future planetary systems assembling in dusty disks. The architecture of planetary systems appears to be more diverse than anyone expected. The solar system, with small rocky planets inside and gas giants outside, is only one arrangement. The Milky Way contains hot Jupiters orbiting close to their stars, compact systems of multiple super-Earths, planets in eccentric orbits, circumbinary planets orbiting two stars, and planets around red dwarfs packed into tight resonant chains. This diversity tells us that planet formation is dynamic and sometimes chaotic. Planets migrate through disks. They scatter each other. They can fall into their stars or be ejected into interstellar space. The galaxy is not producing copies of the solar system. It is producing an enormous range of planetary experiments. The sun's stability is one of the quiet reasons Earth has had time. Massive stars live too briefly for complex planetary evolution as we know it. Very active young red dwarfs may strip atmospheres from close planets. Binary systems can complicate orbital stability. The sun is not rare, but it is well placed in several ways. Long-lived enough, quiet enough, metal-rich enough, and located in a relatively calm region of the galaxy. None of this guarantees life, but it gives time and stability, and time may be the rarest ingredient for complexity. A galaxy can contain billions of planets, but only some will remain stable for billions of years in conditions that allow chemistry to keep building. The Drake equation, often discussed in the search for extraterrestrial intelligence, is less an answer than a framework for uncertainty. It asks how many communicating civilizations might exist in the galaxy by multiplying factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets, the fraction where life begins, the fraction where intelligence develops, the fraction that produces detectable technology, and the length of time such civilizations remain detectable. Some of these factors are now better known than when the equation was proposed. We know planets are common, but the biological and technological factors remain almost entirely unknown. The Milky Way could be full of life, or it could be nearly silent. At present, the honest answer is that we do not know. The Fermi paradox grows from this uncertainty. If the galaxy is old, and if technological civilizations are common, why do we not see clear evidence of them? Many explanations exist. Life may be rare. Complex life may be rare. Technological civilizations may not last long. They may not use detectable signals. They may choose not to broadcast. Interstellar travel may be far more difficult than imagined. Or we may simply not have looked long enough, carefully enough, or in the right way. The Milky Way is large enough that silence is difficult to interpret. Absence of evidence across such distances and timescales is not yet evidence of absence. It is a question suspended across the galaxy. Radio searches for extraterrestrial signals focus partly on the fact that radio waves can travel across interstellar distances and that certain frequencies, like the hydrogen line region, are naturally significant to astronomers. But the galaxy is noisy. Pulsars, quasars beyond the galaxy, human satellites, interstellar plasma, and instrumental effects all complicate the search. A true signal would need to be narrow, persistent, or repeating, and distinguishable from natural phenomena and human interference. The famous WOW signal remains intriguing because it looked, briefly, like the kind of narrowband signal one might hope to find, yet it never repeated. The Milky Way may contain signals we have not detected, or none at all. The search itself is an attempt by one young technological species to ask whether the galaxy contains others. Even without detected life elsewhere, the Milky Way has already produced intelligence at least once. That fact is easy to overlook because it is us. From the galaxy's perspective, the emergence of a species capable of measuring parallax, detecting the galactic center in radio waves, imaging a black hole shadow, mapping a billion stars, and reconstructing ancient mergers is remarkable. The Milky Way has become locally self-observing. A small part of the galaxy, made from its own enriched matter, has begun to map the structure that made it. This does not make humanity central. It makes the process strange. The galaxy has produced, at least once, a way of knowing that it is a galaxy. The Milky Way's future will eventually become dimmer, but not empty. Long after massive stars stop forming, red dwarfs will continue to burn. White dwarfs will cool. Brown dwarfs will fade. stellar remnants will orbit through a darkening galaxy. If protons are stable, matter will persist for unimaginable spans of time. If they decay, even stars and planets will eventually dissolve into lighter particles. On timescales far beyond ordinary astrophysics, gravitational encounters will eject some stars from the galaxy and drive others toward the central black hole. The bright spiral Milky Way is therefore a temporary phase. Like every structure in the universe, it has a youth, maturity, old age, and eventual transformation. But tonight, the Milky Way is still bright. It still forms stars. It still has spiral arms. It still carries the sun through the Orion Spur. It still contains the molecular clouds that will become future systems, the ancient clusters that remember the early universe, and the invisible dark matter halo that holds it together. It is not finished. It is not frozen. It is a living astrophysical system in the non-biological sense, active, cycling, changing, and maintaining patterns across enormous timescales. The galaxy is not a photograph. It is an event that has been unfolding for more than 13 billion years. This is the structure we inhabit, a barred spiral galaxy in the local group, one of countless galaxies in the observable universe, moving through the cosmic web while carrying within it old stars, newborn stars, molecular clouds, dark matter, dust lanes, stellar streams, black holes, planets, and the quiet outer arm system where Earth turns to night. On a dark, clear night, away from city lights, the Milky Way is not a symbol and not a background. It is the galaxy seen from inside itself. The faint diffuse glow is the combined light of billions of unresolved stars. The dark patches are not emptiness, but clouds of dust blocking the stars behind them. The brighter knots mark dense stellar regions, nebulae, and the direction of the inner disk. The whole sky becomes a cross-section through a structure so large that human history is shorter than a flicker against it. There are stars in the Milky Way older than the Earth by almost 9 billion years. There are stars forming now, still wrapped in cold gas. There are white dwarfs cooling slowly, neutron stars spinning in the dark, black holes wandering silently, and brown dwarfs fading almost invisibly into infrared darkness. There are planets we have never seen directly, rogue worlds moving without suns, and clouds that may one day become systems no mind has yet imagined. And somewhere in the outer disk of this galaxy, on a small rocky planet around a medium star of no particular distinction, matter has organized itself into the capacity to look back at the galaxy and understand something of what it sees. That is one of the more extraordinary things that has happened here. The Milky Way turns slowly. The sun moves with it. The Earth moves with the sun. And tonight, beneath all of that motion, the mind can become quiet for a while. Sleep well. Good night.